Imagine, if you will, the universe, moments after the Big Bang. Particles and antiparticles, spontaneously created, dancing in a primordial soup. As the universe cooled, these cosmic ingredients fused together, forming protons and neutrons. Antimatter and matter clashed and annihilated each other, leaving behind an excess of protons and neutrons. This event marked a shift, a cosmic asymmetry which shaped the universe as we now know it. But as this landscape of matter settled, something else, something truly extraordinary happened. And that's a story for later. What's up, my amazing and curious folks? Are you ready to unravel some cosmic mysteries together? I'm your host, Cesar, and joining me is our brilliant commentator, Sonia. Say hello, Sonia.
Hey there, everyone. Excited to be on this cosmic journey with you all.
Absolutely. And don't forget to subscribe to our podcast, Curiosity Wonderland, and hit that bell icon so you never miss an episode. Let's dive into the mysteries of the universe together. Now let's rewind back to the very beginning. Picture this, the universe, a mere 25 microseconds after the Big Bang. At this moment, the universe was in the throes of creation, crafting all the particles and antiparticles it was ever capable of producing. It was at this time that it reached its highest temperatures ever. Unstable, heavy particles decayed, while quarks and gluons banded together to form protons and neutrons. But that's just the start of the story. At these early stages, the universe was a hot, dense soup of protons, neutrons, high-energy photons, and neutrinos. But it looked far from the universe as we know it today. So how did we get from there to here? Well, the next stage involved saying goodbye to the last of our antimatter, which at that point was incredibly abundant. You see, in the fiery heat of the young universe, particles, antiparticles, and unstable particles could be spontaneously created. This resulted in a sort of primordial particle and antiparticle soup. While the laws of physics are largely symmetric between matter and antimatter, it's clear that today's universe is filled with matter and nearly devoid of antimatter. This indicates that any asymmetry must have been generated in the very early universe, shortly after the hot Big Bang. But here's something fascinating. You can always make antimatter in the universe, provided you have enough energy. Einstein's most famous equation, E equals mc squared, allows us to create energy from pure matter by reducing the amount of mass present, such as by annihilating equal parts matter with antimatter. Alternatively, it also lets us create new matter from pure energy, as long as it makes an equivalent amount of antimatter for each matter particle it creates. So in the early universe, the creation and annihilation processes balanced out, as long as there was enough energy for creation to proceed smoothly. Interesting, isn't it? In the beginning, when the universe was incredibly hot, all particles and antiparticles within the standard model could be easily created. Even the most massive particle, the top quark, could be created with ease, provided there was more than 175 giga-electron-volts of energy available for new particle creation in each collision.
So it was like a wild particle and antiparticle creation fest.
Exactly, a wild party indeed. However, if the universe falls below a certain energy threshold, creation would cease and there would be only annihilation.
So as the universe cooled, this creation party started to wind down, right?
Precisely. As the universe cooled, it got less and less likely to spontaneously create new particle and antiparticle pairs. The heaviest pairs disappeared first, and eventually it became impossible to spontaneously create even the lighter ones like muons.
Muons, are those like electrons?
They're similar but more massive. Around the same time, muons decayed, quarks and gluons bound together to form neutrons and protons.
And what happened to the antimatter?
Antiquarks bound together to form antineutrons and antiprotons. After most of the quark and antiquark pairs annihilated, the remaining matter particles formed protons and neutrons amidst a background of neutrinos, antineutrinos, photons, and electron-positron pairs.
So the universe managed to keep itself electrically neutral?
Yes, indeed. There was an excess of electrons over positrons to exactly match the number of protons, ensuring the universe remained electrically neutral. The onset of the hadron era or confinement meant that protons and neutrons could no longer be created freely, but rather as whole protons or neutrons. And that's how we transitioned from a hot, fiery particle soup to the universe we know today. So, here's the next twist. The energy available in the universe became too low for the creation of protons and neutrons, so all the antimatter, in the form of antiprotons and antineutrons, annihilated away with as much matter as it could find. However, there was an excess, about one extra proton or neutron for every 1 4/10 billion proton-antiproton pairs. Now all these annihilations gave rise to photons, the purest form of raw energy, along with all the other annihilations that had happened before. With photon-photon interactions still going strong, they spontaneously produced both neutrino-antineutrino pairs and electron-positron pairs. Even after all the antiprotons and antineutrons disappeared, the universe was still rich with antimatter in the form of antineutrinos and positrons. As the universe expanded and cooled, unstable particles and antiparticles decayed, and matter-antimatter pairs annihilated, and photons could no longer collide at high enough energies to create new particles. Imagine the universe at this stage, only tens of microseconds after the Big Bang, with particles packed tighter everywhere than they are today, even within the center of our sun. Temperatures would be in the trillions of degrees, more than 100,000 times as great as in the sun's core. It's a truly stunning concept, isn't it? The raw, tempestuous beginnings of our universe, filled with particle-antiparticle pairs, rapidly annihilating and creating, with temperatures hotter than the core of our sun. Just take a moment to let that sink in. I find it utterly fascinating how the world of science can transport us back in time to the very beginning of the universe, through theory and evidence. What do you think, dear listeners? Isn't it mind-blowing to think how far we've come in our understanding of the beginnings of the universe? I love hearing your thoughts, so don't forget to share them in the comments section. I hope you're enjoying these incredible discoveries as much as I am. Now, even after the electroweak symmetry breaks, weak interactions continue to play a vital role. In the hot, dense, early universe, weak interactions enabled protons and neutrons to convert into one another. As long as the universe was energetic enough, 4 key reactions could occur.
Wait, are you saying that protons and neutrons were casually swapping spots?
Exactly. As long as the weak interactions and energy allowed, these reactions could proceed either forwards or backwards. The universe was like a giant particle dance floor.
And as the universe cooled, I'm guessing the music stopped for some particles, right?
Precisely. Quarks, muons, taus, and the gauge bosons were all casualties of the falling temperature. By the time about 25 microseconds had passed, only electron-positron pairs and neutrino-antineutrino pairs were left to dance.
So despite all that chaos, balance was maintained.
Yes, as long as temperatures and densities were high enough, all of these reactions occurred spontaneously and at equal rates. It's a fascinating testament to the delicate balance of the universe. Let's continue our journey. For about the first full second after the Big Bang, everything was in equilibrium. And when I say everything, I mean the whole universe was interconverting protons and neutrons at will, giving us about an equal split between protons and neutrons. Think of it as a cosmic tug-of-war, with each conversion between a proton into a neutron being mirrored by a neutron being converted into a proton. These reactions were happening at about the same overall net rate. However, as always in the universe, change was on the horizon. As the energy within each particle dropped, it became just a teensy bit more energetically favorable to produce a proton than a neutron from these interactions. Now, why was that? Well, remember, the neutron is a tad more massive than the proton. So, when the temperature of the universe dropped to a value that corresponded to that energy difference, the proton population began to slightly dominate the neutron population. This shift occurred right around the time the universe reached an age of 1 second. Yes, dear listeners, all this we're discussing happened in the first second after the Big Bang. Quite an eventful second, wasn't it? And that second set the stage for 2 additional, pivotal events. First, the weak interactions froze out, meaning the proton-neutron interconversion interactions stopped. So while it may seem like a short stint in time, that first second after the Big Bang significantly shaped the course of the universe. It's remarkable, isn't it? Every tiny event, every interaction was a critical piece in the grand puzzle of our existence. So as the universe cooled down, neutrinos and antineutrinos stopped interacting. This meant that they essentially ignored everything else in the universe.
Almost like they're in their own little universe within the universe.
Exactly. These neutrinos and antineutrinos should still be around today, with a kinetic energy that corresponds to a temperature just above absolute zero.
So they were created in the heat of the Big Bang, but now they are almost as cold as possible.
Yes, quite a journey, isn't it? But let's turn back to the energetic universe for a moment. Two photons could still collide and spontaneously produce electron-positron pairs.
And this could only happen while the universe was still pretty hot and dense, right?
Right. And this continued until the universe was about 3 seconds old, just slightly after the weak interactions froze out.
That's another critical moment, isn't it?
Absolutely. All the energy that was tied up in electrons and positrons went exclusively into photons. This represents the universe losing the last of its antimatter.
So our universe was left with no antimatter?
Well, not quite. Only antineutrinos remained, and they persist even today. This event had a big implication for the temperature of what we now know as the cosmic microwave background.
Let me guess. We've detected this background and confirmed these predictions.
Spot on. We've measured their temperature, and they match perfectly with these explicit predictions from the Big Bang. The universe, my friend, is a symphony of physics. You know, the cosmic microwave background, or CMB, was first detected in 1964, but it took until 1992 to accurately measure its temperature.
Isn't it fascinating how long it can take to fully understand something that we've discovered?
Absolutely. And it's not just the CMB. The imprint of the neutrino background on the CMB and the universe's structure was only detected in 2015.
So we're still making new discoveries about the early universe.
Indeed we are. You know, your comment reminds me of a recent event. I was reading a paper about an astrophysicist's findings. He had discovered a phase shift in the CMB's fluctuations that allowed him to determine how much energy the neutrinos would have had at the early stages of the universe.
Oh, what a coincidence! I was just talking to a friend about this. She's a physics teacher and was telling me about a similar experiment her students were conducting.
Well, as they say, the universe is full of surprises, and in this case, it's a surprise that sheds light on our cosmic history. The cosmic neutrino background was found to have a temperature of 1.96 K, in perfect agreement with the Big Bang's predictions.
It's amazing how these tiny details can have such profound implications for our understanding of the universe.
Profound indeed. Each discovery, each tiny piece of the puzzle, brings us one step closer to understanding the grand symphony that is our universe. Now, after the first 3 seconds following the hot Big Bang, the universe was no longer split evenly between protons and neutrons. The ratio had changed dramatically, favoring protons over neutrons by about 85 to 15.
That's quite a shift.
It sure is. And while neutrinos and antineutrinos had completely decoupled from other particles, they were still in the universe, moving through space freely at speeds indistinguishable from, but slightly lower than, the speed of light.
So, they were off doing their own thing, so to speak.
More or less, yes. Meanwhile, the positrons or anti-electrons were all gone, and so were most of the electrons.
And what was left in terms of electrons and protons?
Good question. When all was said and done, there were exactly as many electrons as there were protons, maintaining the universe's electrical neutrality.
And the universe's balance was restored.
Yes, in a way. But remember, there were also over 1 billion photons for every proton or neutron, and a background of about 70% as many neutrinos and antineutrinos as photons.
So the universe was still quite crowded.
Yes, it was. And though it had cooled tremendously in just the first 3 seconds, it was still hot and dense. But with all the antimatter gone, the raw ingredients to begin building the universe as we know it were finally in place.
So, this was the beginning of the universe we recognize today?
That's right. The stage was set for the universe as we know it to start taking shape. So just to recap, at the start of the universe after the hot Big Bang, a particle-antiparticle soup was formed with a slight excess of matter. As the universe cooled, these particles grouped, forming protons and neutrons, while antimatter was annihilated, leaving a surplus of protons and neutrons.
And then, as the universe continued to expand and cool, an event occurred that led to the annihilation of the remaining electrons and positrons into photons.
Correct. Only the antineutrinos persisted as antimatter in the universe. We also discussed how the cosmic microwave background, or CMB, which is hotter than the neutrino background, played a pivotal role in shaping the universe as we know it.
So it seems like the universe, in its earliest moments, baked a recipe with the perfect ingredients to create, well, everything we see around us.
That's one way to put it. It's like the universe was playing chef in a cosmic kitchen.
Right you are. Well, it has been a pleasure exploring these cosmic mysteries with all of you. If you enjoyed us breaking down the universe's recipe, be sure to blast that like button and drop a comment below.
And don't forget to share this episode with your friends. Spread the cosmic knowledge.
Absolutely. Thank you so much for joining us today on this journey through time and space.
That's all from us for today. This has been a truly astronomical episode. Until next time, keep reaching for the stars.
Goodbye, everyone, and take care.
This wealth of information comes courtesy of an article titled, "What Was It Like When the Last Antimatter Disappeared?" by Ethan Siegel, published on Big Think on November 29, 2023. You can find the full URL in the video description if you'd like to delve even deeper into the topic. All right, folks, that's it from me. See you next time.